Welcome back. Calculus Conundrums, limits by the perfect square. Now we're going to continue on using the replacement theorem to evaluate limits, but this time I'm going to show you that when you have radicals, it's best to use the rationalization technique. So let's take a look at a couple of examples. This first example says find the limit of the square root of x plus 1 minus 1 all divided by x as x approaches 0. Now if you tried to evaluate this directly, you get square root of 1 minus 1, which is 0, so you would get 0 in the numerator, and then of course if you let x be 0, because x equals 0, so you would get 0 in the denominator. So we get that 0 over 0, which is an indeterminate form. So the trick here is to realize that I look up here and I see this radical square root of x plus 1 minus 1. And if you think about it, you know, what is the conjugate of this guy right here? The conjugate of square root of x plus 1 minus 1 is this guy right here. Let me just highlight it with this. So that would be the square root of x plus 1 plus 1. So in other words, if I multiply, and we learned this in algebra, if you multiply this square root minus 1 by this same square root plus 1, it will eliminate the radical. So now let's see what happens when we do that. So when we multiply this, you're really multiplying difference of perfect squares. So you have square root of x plus 1 times square root of x plus 1, which will just give me x plus 1 right here, and then minus 1 squared. So I would get minus 1 squared, which is minus 1. And then of course, then you can say, okay, well the minus 1 and the plus 1 cancel, so all I have in the numerator is x. Now, let's not forget the denominator. If I multiply the numerator by square root of x plus 1 plus 1, I have to multiply the denominator by square root of x plus 1 plus 1. So I'm just going to show that down here, and that's important that you don't try to distribute the x through, because the x is actually going to cancel with the x in the numerator, and if you distribute it through, you might lose that x and not see the cancellation. So we're just going to leave this the way I've written it here, x times this expression. So now go over here and I have x in the numerator, and in the denominator I have x times this expression. And so we know that I can cancel x over x and just get 1. So then I would have 1 over square root of x plus 1 plus 1. So that would be my replacement function. So then I could go down here, and remember I wanted to find the limit of this function as x approaches 0, but I saw that I could replace that limit with this function as x approaches 0, and now I can evaluate the limit of this function directly by just letting x be 0. So if I let x be 0, I get 1 over square root of 1 plus 1, and since square root of 1 is 1, I get 1 over 1 plus 1, which is simply 1/2. So my answer there is simply 1/2. Okay, here's another one. This is actually very similar to the one I just did, so maybe I don't need to cover it in detail, but I have a square root of x plus 2 minus square root of 2 all over x. And if you plugged in 0 for x, you get square root of 2 minus square root of 2 on top. And then if you let x be 0 on the bottom, you get 0 on the bottom. So you would get that 0 over 0 form. So again, I have a radical in the numerator here. So I have square root of x plus 2 minus square root of 2. Now here I actually have two radicals, so when I multiply by the conjugate is actually going to be square root of x plus 2 plus square root of x, square root of x plus 2 plus square root of 2. So I multiply the numerator by that, and I also multiply the denominator by that. Now, when you multiply the two numerators together, you're going to square the square root of x plus 2, and you'll just get this x plus 2 right here. And then you're going to have minus, and you're going to square the square root, so you'll have minus 2. And then all you have to do is cancel the 2's, because 2 minus 2 is 0. And then on bottom, I just show that I have x times this expression. Remember, don't distribute the x, just leave it like this. And then when I come down to my next step, I have x in the numerator and x in the denominator. And just like I did before, I can cancel these and get 1 in the numerator. So now I have 1 over square root of x plus 2 plus square root of 2. And then if I go back to my limit, here, I can replace the function in this limit with the function in this limit. And then when I let x be 0, if you plug 0 in for x, you get 1 over square root of 2 plus square root of 2, which of course is just 1 over 2 square root of 2. And that's your final answer. And that's the answer that you're going to want to put. Now, I know some of you might want to try to look at the graph of this function and try to estimate what, using a decimal value of what this equals as x approaches 0, but you're going to get it counted wrong if you do that, because your instructor is probably going to want the exact answer, which is 1 over 2 square root of 2, and the only way you can get that is by using this rationalization technique. Okay, I'm going to finish this video up, just show you a couple of examples. Here you'll see 2 examples. I'm just going to work the first one. The second one is very similar to one I did on the previous video. It's very similar to this one that had x cubed plus 27. That's on the previous video. So I'm not going to work this one. You can just go through my work on this one. I'm going to go ahead and work this one for you. And this, now we're going back to cancellation, factoring and cancel. So here, again, if you can plug 0 in and see that you'll get 0 over 0, so we can't determine the limit that way. So what I'm going to do is I'm going to factor the numerator and denominator. So let me show you. Here's my function. If I factor the numerator, I get x times x minus 25. And then if I factor my, hang on just a second, something's off on this one. Okay, I take it back. It's fine. I was thinking that I was going to cancel the x minus 25, but actually what I'm going to end up canceling here are just the x's. So here I can cancel this x with this x, and then in the numerator I just get x minus 25, and in the denominator I get 2 times x minus 5. So I can take this function, the limit of this function as x approaches 0, and I can replace it with the limit of this function as x approaches 0. And when I do that, if I let x be 0 here, I get minus 25. And if I let x be 0 in the denominator, I get 2 times negative 5, which is negative 10. So I have negative 25 divided by negative 10, which is, that actually reduces to positive 5 halves or positive 2.5. Okay? When you start talking about derivatives, you're going to see a limit very similar to this, where you take the limit of a difference quotient. So I'm going to go ahead and evaluate this limit next, so you can kind of be prepared when you get into derivatives. So again, if you let h be 0, you get square root of 3 minus square root of 3, which is 0 in the numerator, and you'll also get 0 in the denominator. So we get that indeterminate form. So what I'm going to do here is, since it involves radicals, I'm actually going to multiply this function here by the conjugate square root of 3 plus h plus square root of 3 all over itself. And then when I multiply the numerators together, you square the square root of 3 plus h, and that gives you 3 plus h. And then you subtract square root of 3 squared, so that's going to give you minus 3. And then what you can do there is you can cancel, and you'll just get h in the numerator. And remember, in the denominator, don't multiply this together. So we get h times this and h times that. So in the next step, we can actually take this h and cancel it. Whoops, I lost my h there. Okay. I jumped the gun there. So I've still got an h. I got an h in the numerator. I got an h in the denominator. So now I can cancel those h's. And now I get 1 over square root of 3 plus h plus square root of 3. And now if you let h go to 0, you can now evaluate this directly, and you get 1 over square root of 3 plus square root of 3, which is 1 over 2 square root of 3. And so that's your final answer for the limit. I'm going to wrap this up with some trig limits. So again, if you're in Calculus 1, you probably need this, but otherwise you probably don't need it. So what I'm going to talk about here, first of all, let me just show you two important trig limits that you can just kind of put into your arsenal. The limit of sine x over x as x approaches 0 is 1, and the limit of 1 minus cosine x divided by x as x approaches 0 is 0. So just take those on faith. I'm not going to prove them to you. I'm just going to show you a couple of examples here, and I'm going to go through these rather quickly so I can squeeze them all in. So if I take the limit, if I tried to evaluate this limit directly, I would get 0 over 0. So what I'm going to do is I'm going to factor sine x out of the terms in the numerator, and I'll get sine x times sine x minus 1 over x. And then I can break this up as sine x over x and sine x minus 1. So I can break this limit up into two limits, the limit of sine x over x and the limit of sine x minus 1. And then the limit of sine x over x, we just saw that equals 0. That equals 1. The limit of sine x over x is 1. And then if you plug 0 in here, you get sine of 0 minus 1 would give you minus 1. So you'd have 1 times minus 1 is negative 1. The second one here, you can factor these using difference of squares, and this factors into 1 minus cosine x times 1 plus cosine x. And you can break that up into the limit of 1 minus cosine x over x times the limit of 1. That actually should be 1 plus cosine x. So let me correct that. Okay, so that should be a plus right there, 1 plus cosine x. So we know from above that this limit is equal to 0. And if you plug 0 in here, you get 1 plus cosine of 0, which is 1 plus 1. So you get 0 times 2, which is still 0. This one, sine 5x over x, again, if you let x be 0, you would get 0 over 0, which is indeterminate. What you can do on this one is you can actually multiply the numerator and denominator by 5. And then that way, this part right here, you can change it to a different variable. I'm going to call it u. And so now this would be sine u over u. And we know that if x goes to 0, then 5x goes to 0. So we can write this as the limit of sine u over u as u goes to 0. And that would be 1. And then the 5 that I had in the numerator, I factored it out. So I'd have 5 times 1, which is 5. And then the last one, the limit of tangent x over x as x approaches 0. Well, tangent x is same as sine x over cosine x, so I can write this as sine x over cosine x, and I still have this x in the denominator. And then I can break this up into two limits, the limit of sine x over x as x approaches 0, and then the limit of 1 over cosine x as x approaches 0. And we know the limit of sine x over x is 1, and the limit of 1 over cosine x is just 1 over cosine 0, which is 1 over 1. So you end up getting 1 times 1, which is 1. And so that ends this video. So that ends this video on the replacement theorem. And the next video, I'm going to talk to you about one-sided limits. So I'll introduce that concept in the next video.